Okay. You tell me when I can start. Can I? So good morning, everybody. Calimera. So I think that we can start. Let me recap what we saw last time, yesterday. The very last point was the pooling operator. So recall that the goal of pooling is to shrink a graph. So we have possibly a large or not a large graph, and our goal is to shrink it. And when we do this is, so we saw yesterday that we have three major aspects that we need to do after. The first one is how do we need to group together the nodes? So how do we do the aggregation? The second point is once we have the new shrink graph, which are the features that we should assign to the nodes and to the edges? And then how do we connect the new nodes in order to build a graph? So these are the 3 points. So we start by introducing a framework, which is grouping all the methods, the plethora of methods that we saw yesterday. So I was presenting a slide with at least tens of different methods for pooling. Within this approach, all them they shrink together in 3 steps. The first one is the select step. And in the select step, the goal is to aggregate nodes. So we just look at the topology. And just to get the flavor, to understand it. So we can use some very trivial methods. One possibility, we have this graph. And what we want to do is a partition. So we make a partition of these nodes into sets. This one will degenerate in one node. This one will degenerate in another node. And this one will degenerate in another node. Okay, partition. Mutually independent, mutually exclusive. Or we might have some possible covers, overlaps. So we partition these nodes, but a node can be in 2 sets, which means that it is so relevant that we decide to keep that node in one meta node and also in another one. So in this case, for instance, we have this purple node, which goes in this meta node here and also here. And then, of course, we will need to decide how to assign the features to the nodes, how to connect the nodes, but that is those are different steps. A third method, and as again, I was saying, these are some intuitive but trivial methods, trivial approaches, is to use a sparse approach where basically you sample from the set of nodes and you keep some of them according to some needs. Most of times these methods are based on some estimate of the density of the nodes with respect to space. If you have several sensors, each of which is a node, and they are close in space, by doing a sampling, you might keep the relevant information. In reality, what we want to do is something more complex, and we will see that by doing this consideration, we will be able to learn how to group nodes. So this selection stage, the selection operator, aims at taking the graph, the nodes of the graph, and partition them into a new set or a subset of them. So basically, at the end of the day, what we would like very much is to generate these sets. And this one, the first set will degenerate in one meta node, this one in the second meta node, and this one in the third meta. The key point is to pass through a matrix, which is called the score matrix, which is this S. And this S has, here you have the number of nodes. And here you have the number of meta nodes that you want to keep. So you want to keep, for now, I'm imposing, I want, like in clustering, you say K means I want K. So you set K. We want a K meta nodes, and here we have the N starting nodes. We color, with the color means that in the first meta node, which is this line, we have this blue, this pink, and this orange. In the second meta node, this is a meta node, you have this one, and this one. In the third, in this case, K is equal 3, you have only one node, which is the error. Okay, that is a score matrix. What you have here are not the attributes. What you have here is that node is part of the set. That is the information. And then you might say, is that a binary? It's not binary. Is that exclusive or not? Well, it's not necessary because you might have one blue here, one blue here, one blue here. So the blue is so relevant that it is in the 3 places with different contributions, because that is the idea. And which is the contribution? Should they be full? No, not necessary. They will be part of that meta node with a contribution which will depend on edges and attributes. Okay, that is the general idea. But since we don't know this score matrix, we will learn it. Okay. But before learning that, let's look at how to do the partition, how to group and generate, how to generate these partitions, and then these score matrix. Okay, so there are a set of methods before try to learn the score matrix. So some examples, just to show you what is in the literature. One is called the spectral clustering. So you have a graph, and this is done, for instance, in social networks. You have a huge graph, whatever is in there. You have all the nodes, and what you want to do is to start grouping them. Now, by looking at the topology only, not at the information associated with the graph, you can use some spectral approach. And in the spectral approach, what you do, you look at the graph, you take the Laplacian matrix, and you compute the eigenvectors. It can be shown that if the graph has some structure, then the eigenvectors are very much related to a Fourier transform. So they are very much related to the frequency component of the Laplacian. Okay. Under this comment, what you see is for this graph, for instance, you have 20 nodes, and this is the eigenvector associated with the first low frequency. So what you see is looking like a sinusoidal. It can be that, it can be different, depends on the eigenvector, not eigenvector, okay? Eigenvector. And if you look at this, you see clearly that there is a split into halves. So if these are the 20 nodes composing this graph, you have a set which are positive in the value of this eigenvector and others that are negative. So if you want, you can split into subsets. And that is the idea. Or what you can also do is not only considering the one eigenvector, but a number of eigenvectors, and then you use those features in order to do clustering. You can use KIOS, for instance, and then you group them. Another approach, which is very much related, sorry, no, this is back and forth in the morning. Another approach, which again is related to a spectral clustering, is called the node decimation. And what you do, you consider the eigenvector associated with a very high frequency. And if you look at this eigenvector for this graph, well, this is an example, it looks like this. And what you see again is that you have nodes that are positive and nodes whose value in the eigenvector are negative. Well, you can decide to keep only a subset, only the positive or only the negative ones. And this is called the decimation. It's a spectral decimation. In between, there is a plethora of where is the real problem with these methods? Well, at first is that you needed to compute eigenvalues and then eigenvectors, and the cost is cubic with the number of nodes. Very expensive. If you have a social network where you will have, I don't know, thousands, millions of nodes, you can imagine that. And the second problem with these methods, though they are effective, so we should not ignore them by definition, is that they don't consider the attributes, the features. So they just look at the topology of the graph. They are based on the Laplacian only, not at the features. Though, if the graph has been built by looking at the functional dependencies, so we are related because we know that, the topology plays a very relevant role. And that is why these methods are used. Okay, and then we will come back because we want to learn this step. The second stage is a reduce. Okay, now in some way, for instance, with the spectral methods, we were able to generate the meta nodes, the subclusters. And now what we want to do is to assign the attributes at the node level, at this group of nodes. So I put together the mouse, this one and this one, they belong to the same cluster, the meta node. If they have their own features, which is the feature that we should consider for that node? So we should blend somehow the features. Okay, that is it. This step is called the reduce. We go back. So the idea is we have seen that the reduction has to say that now we have this meta node. Inside we have the nodes with the attributes. And we want to generate, we know that, one node with some new attributes, which will become blended from these ones. Okay, that is the idea. So a typical approach is based on the score matrix. So the score matrix was saying you belong to this cluster, you belong to this cluster. And it is intuitive to consider as a first step that the new weights will be a linear combination of these features, where the linear combination is weighted according to the score matrix. What does it mean? That if in the score matrix I'm saying that the first node, the blue one, accounts 1/3, and another one, I don't know, 2/3, 4/5, whatever it is. So they have different weights, so that at the end it will be 1. Then what I do, I say that the new features are linearly dependent, is a linear combination of the features original in the node set. And in order to do that, what we say is that the new features is just a linear combination according to the score matrix. Very simple. Why is this important? Because when we will learn the score matrix S, we will have a way to automatically nicely compute what we have. Well, the third step is the connect. So in the connect, we have these, again, meta nodes. In the reduce, we were able to assign some features at the node level. And now we want to link, to create the connection. And in order to do that, what we can do is that the new topology in prime, this is the topology adjacency matrix, is this product, so of the original matrix, adjacency matrix, weighted, rotated somehow through the score matrix. So you do, you apply this transformation and you get one. But under the assumption that everything is linear, that you want to keep it in the balance. So if we look at what is going on, we see that if we put everything together, we see that we have this selection approach that starts from the original graph. Selection will provide the score matrix S, the assignment. This one is a function. And if it is a function, we can learn any function if needed. The reduction. The reduction is also a function that takes the original graph and the partition, if we wish, and we generate the new set of features to be assigned to this subgraph. And then finally, the connection, which is taking all previous information. It is again a function that is generating the new connectivity and also the information associated with edges. Okay. Again, pooling methods. Which are the different pooling methods present in the literature? And then again, I told you, I anticipated that I will show a method which will consist in learning the score metrics and all the other things. But in the literature, what you see is that there is a huge amount of methods doing pooling. Clustering at first, so select, and then you reduce, you assign the features, and then you connect. And these methods are based on different approaches. On mean cut, they try to generate all methods coming from graph processing in a way. And they look at the connectivity, at the degrees of the connectivity between the nodes, and this is graph groups. Or they try to merge together the clicks, if you have clicks within the graph, and then they find a way to provide features. Or they look at the local density with respect to the Laplacian. I'm not going into the very fine details. I'm just telling you that there are different methods which depend either on the topology or on the connectivity, how dense is a node with respect to the neighbors, and so on. Or you can start learning to pool. And this is what is very relevant to us, because all existing methods, they are making assumptions. So if it is true that there is a local density, blah, 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 blah. If it is true that we can linearly combine the different elements, blah, blah, blah. Okay, everything is sound from the theoretical point of view, but sometimes you lose in effectiveness in the method. So a deep approach is to say, well, okay, I don't know which is the grouping I should consider. Let me learn it. And if we look at this approach, so the idea is to learn these score metrics, basically. And there are different methods. One is the pool. You try to regularize the prediction for the loss. One of the most interesting is the mean cut. Why is this interesting? Is because you want to cluster by trying to follow the mean cut problem, which is a classical problem in graph theory, where you want to cut to partition so that the volume, the connectivity between the new cluster and the new cluster and the outside is minimized. So you want to cut the minimum number of edges. And and then there are many others that do combine different techniques. So for the mean cut, basically what you want to do is the following. So again, I'm just introducing the mean cut because it is something that the mean cut is a concept coming from the graph theory, which is very neat, well structured. So basically, you have a mean cut loss, which is this term. Basically, what you say is that you would like to cluster so that in the new graph, the cut will be minimal with respect to the previous one. And if you look at this, here you have the numerator, the volume, the links that you need to cut, the volume of the links that you need to cut with respect to the links which are part of the cluster, of the original cluster. So this is the traditional loss function. And then what you want to do is to learn the score matrix S, because the score matrix will allow you in the select to do the partitioning. And then you might use this linear projection to define the new features, and then you will consider this approach in order to generate the new adjacency matrix. However, if you minimize this loss end-to-end, because here you have a multi-layer perceptron, which is generating and providing the score matrix, you end up with trivial solutions sometimes. So either you cut everything or you don't cut everything, so you need to balance. You would like to say that what you provide is possibly sparse, and you would like to minimize the number of nodes that stay in 2 or more than 2 megaclusters. And this comes through an orthogonality loss, which is this one, which is weighted to the mean cut loss through a Tikhonov regularity. So you put everything together, and then end-to-end, so everything is differentiable, you learn these score metrics. When you have the score matrix, you have the clustering, you have the new features, and you have the new adjacency matrix. This is a method which is proven to be very effective. The problem associated with these type of methods is that they tend to generate dense frameworks. With dense, it means that one node in probability belongs to many clusters. You would like differently to try to have one node to belong, if possible, to the minimum number of meta nodes. And so how can we do that? So in order to impose that constraints, wishes, because it is a wish to do something like that, because we want to get a sparse selection, we needed to consider methods which are based on the top K. Let's look at it. In a top K, you have, let's say, the features. You apply a nonlinear stuff which provides the score. And this score basically says this node should belong to this cluster. This node should belong to this cluster with some probability and so on. Or you might say, I want to keep only the nodes that maximize this. if someone node through this nonlinear function is not maximizing something, is not so relevant in the economy of the new graph, I want to discard it. And I want to keep only the top k scores, the most relevant ones. All the others, they are discarded. So what do? You sort the scores. Clearly, you have a nonlinear function here, which will be learned. So it's like in a bank when you have the transactions and you want to detect the fraud transactions. So you provide a score per each transaction. You sort the scores and then you focus on the top k. That's it, the very same concept. So you want to focus on something that where you believe that there is value. If there is not value or less value, you discard it. The energy is finite. Your efforts have a value, have a cost. So you sort them, and then you keep these top scores, which means that you keep the top k units, and they will be part of the adjacent sequence. Okay, so this is what is going to happen. And for the others, you discard them. There are many other methods. There are many methods that do this, and in order to select and to learn what to keep and what not to keep, there are methods that look at linear projections. So they try to identify parameters like inattention. I want you or I don't want you, basically. You can do the selection with a graph neural network too, which means that they propose some nodes to be relevant than others. So there are different techniques which allow you to come back with a proposal. The problem with these methods, anyway, is that most of times they are not differentiable. If you take the top k and you want to differentiate that, so you needed to find solutions which allow you to apply the gradient descent in some way. So many tricks. And the literature tries on one side to be able to impose the fact that you want to learn something. And on the other side, the methods try not to have some dense topologies. So you want your final graph to be as sparse as possible. And they do that through different methods. So dense versus sparse, fixed versus adaptive. Should I adapt my clusters over time or not? In some cases, with the attention mechanism, you allow the pooling to be adaptive. So you change the topology of the new graph based on the input. And you activate or deactivate some nodes. So it is not a constant topology. Or they can be trainable or not trainable. But anyway, so to sum up, pooling. Again, I recall that there is a school of thought that says pooling might not be good. And you consider pooling only if it is true that the convolution does make sense, which means that there is a high regularity in the data, the graph is very much connected in a way. Then you do convolution, and then pooling is not going to create disasters. If that is the case, you use that. Or you use pooling, even if you have introduced a loss in information, if you want to shrink the dimension of the graph because it is too large, and then you cannot carry out any computation. So you know you know that probably you will lose information, but you will become, you will build something which is manageable for the population. Global pooling. So this parallelism goes back to the convolutional neural network. So convolutional neural network for images, we have images, convolution, shrink, pooling. Convolution, shrink, pooling. At the end of this deep architecture, you have a set of tiny small images. Let's say 3 by 3, 5 by 5, and they are in a stack. That is the very last layer. Now, what you have to do is to take this tensor and apply that to the classifier, the multi-layer percent, or the regressor, or the predictor, whatever it is. So the global pooling is taking this structure and it is unrolling. So from the 2D, 2-dimension or 3-dimension, you generate a vector that will be used to feed the multi-layer percent. So if we look at this, only one of these tiny matrices, what you do, you buy lines, so you slice it and you put it in a huge vector. This is called the global. And this vector is going to be fed into the multi-layer perception, which depends on your task. Okay, so what you want to do now is something very similar with a graph. So you start from a graph, and what you want to do is to generate a new graph or a scalar, a vector that at the end of the day will be fed into the multi-layer set. How do you do that? Well, you can use, you can sum the average, the different nodes, the features. You can introduce your attention mechanism, because what you have to do is to take every single node of the final graph and transform that into a vector. One possibility is simply to take the features associated with the nodes, or you can do something more complex, so you can select based on the attention. But we go here. So one possibility is I take all these items, I group them together in one node, and then I have a vector, and that is what I'm going to do. Or the other possibilities, you treat differently this data. So you might take the features associated with this node, the features associated with the node. You make it just a position, first vector, second vector, third vector. You generate a long vector, which goes into the multi-layer percent. So you can apply some shrinking operators. You can apply attention, which means I have this graph. I don't want all the nodes, but I want all this node, and this node. So I take these features, these features, I put them together in a vector, and that is what I'm going to provide to the very last layer. Or there are many other things. So I think that with this, we are ending the operators section. I want to show you a demo. If you're interested in these methods, there are two libraries which you can consider. Spectral has been designed by us, and PyG is something available in the open domain. They are tested, so they are valuable, and there you find most of the methods I was presenting to you. That is a very useful way to build and personalize this very complex structure work to your application, if you wish. What I would like to do now is to show an example, a small demo, to see how can we use all these graph neural networks to solve at least one problem. Okay? May I ask you, sorry, can you switch to the, you have the PDF. So if you click on the PDF, you open the Colab, okay? And then there you have the code, and you can go through the code by yourself, but we can do that right here. That's okay, it's connecting. Okay, so these are some demos that I use for my students, but if you go through them, you will see all what I was telling you in a very compact way in order to have some recap of which are the basic ideas. So there is always some preliminaries where we say what we are talking about. We record what is a graph neural network. So if we look at this equation number 1, if you remember, we have the graph shift operator, this A tilde, which is function of the topology matrix, which if you take the power of that, you will consider different levels, hops within your graph. You have the previous state, which is this capital H, which at the beginning will be X, the features of the input graph, and then you have the parameters of the convolution here, the 3 parameters. And then you have a nonlinear function, and you generate the new graph. Okay? Graph, 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 graph. There are no pooling layers here, just convolution. Nonlinear convolution. Okay, so message passing. So we use a message passing. And yeah, so at first we start loading all the packages. The demo, the problem I want to tell you is called Cobra. So it is related to a citation problem. So you have a set of documents, they are around 3,000, which means that you have 3,000 nodes. That is the idea. So a significant number of nodes. Each node is a paper again. And what this benchmark is doing is going through the paper, extracting a subset of features which are related to the presence of some words. Okay, so a bag of words. So you define your dictionary, which is relevant, and then you go inside and say, do we have the word science, technology, computer, you know? And then that is your features. The feature vector, this bag of words, is, if I remember, then we will see 1.4,000, so 1,400. That is the size of the feature vector. So you have, again, around 3,000 nodes, each of which the information associated with each node is a vector of, say, 1,400 components. And they are connected depending on the citation. So if the two papers are cite each other, there is a connection. Okay? They are directional. I'm citing you. You don't cite me, fine. Okay? So they are directed graph. This is the structure. Within this framework, we have, then we will see the numbers, some of them are classified according to the type of the paper. What does it mean? I have this paper, and I'm telling you, because that it is a semi-supervised framework, some of them, they have a label, which is saying which type of paper is in there, so which is the content. Physics, chemistry, literature, blah, 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 okay? 7 classes. But the percentage of labels is very limited. And the majority of the papers, they don't have any classification. What we want to do is, if this is a new paper, and we have the content, how should I classify that? Is that science? Is that geography? Is that history? Okay. It is like when I was saying yesterday, how do people vote? The same concept. So we have this group. Each of you is a sensor. I know what I'm going to vote. I do some interviews. Only for very few people, I have the label.
We know that we are connected through WeChat, for instance, and that is the way we are connected. So we have a graph. Each of us will be profiled, and that is the feature vector assigned to the node. Okay? Now, what we want to do is having this subset of labels all over the graph. What about the others? What are you going to vote? You. This is called transductive learning. So the learning set is part of what you have, and you want to infer something which is part of this framework that has no labels. Clear? So one approach, we don't use graphs, and then we will see what does it mean. That if we are not using graph, no topology, no connectivity, we have a training set, which is supervised learning. So we will have couples only starting from the nodes having also the label. So you take only those papers that having the labels, you build a classifier, and then you apply all the other papers, and you will get some. Okay? And this is the first part of the demo. In the second part of the demo, we will introduce the topology. So we will say, yes, but we can do more than that. There is the topology, they are connected. And that is the prior, that is inductive bias. And we will, so if we have a graph, we will use all the operators that I was showing you, and we will get something else. Okay? Is it clear what we are going to see? So I installed the elements. So this is the number of features, 1,443. We have 7 classes, which defines the category of the document. These are benchmarks. So we know if it's needed. Okay. Some statistics related to the graph. Okay, so basically, the number of nodes, the number of papers is 2,700. The number of edges is 10,000, more than 10,000. So you see, now we have a reason. And you will see that also computation on a GPU is very fast. The average node degree is 3.9, which means that on the average, we have a 3.9 citation. Okay. The number of training nodes are 140 for the 7 classes. So very few of them have a label. Okay. Out of 2,700. So the easiest way, the easiest approach, no graphs, I don't want to consider the graph, is, okay, this is a supervised problem. We want to do classification. We build an architecture, a fit-for architecture, which is this one. It has one layer, one hidden layer. This is the size of the hidden layer, 16 euros. You can play with those numbers. This one is the best configuration, the best configuration. Keep in mind, we have very few training layers. So you consider huge architectures. It won't make any sense. Okay? Okay, so we did this. Okay. So the training completed. Now, okay, so now we are doing training. Already completed. We are on the GPU. The architecture is very small. And now we look at the performance of what the test said. So we have 2,500 documents that have not a label, and we want to see the accuracy. As simple as that. Okay, so the accuracy on the test set is around 60%. Here we are not considering the interval of confidence, blah, blah, blah. This is just a number, okay? Now, can we do more than this? Yes, we know it is a graph. Now, if it is a graph, there is the connection, and the connection comes through the topology matrix. So we want to add the relational inductive bias. So there are connections, there are functional dependencies. And the functional dependency means that we are not only happy to consider and process the input data, the X, because that is what we were doing before, but we have also the topology, which goes through the adjacency matrix. And then we know that from the adjacency matrix, we will move into the graph shift operator because it's more suitable, and so on, through the Laplacian, diffusion models, and so on. The architecture we are considering, which is this one, has layers, which are the ones we have seen. So basically, we are implementing message passing. We have the parameters of the message passing in order to generate the updated graph. So if this one is the message passing, these are the details. So this is the message. We do linear convolution. We aggregate all the messages coming from the universe. And then we apply as an update function, which is a hyperbolic tangent. You can change whatever, so I don't care. It is an example. So, okay, and now what we have to do is to load all the libraries for doing learning in a graph domain. So we import those libraries, having different levels of message passing inside. So you can change the type of message passing, blah, 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 depending on the fabric one. So those are parameters. We use a random walk. And now we consider, again, you can play here, so you can change these numbers, 2 levels of processing. So you have one graph neural network that is doing convolution. So it receives the graph, the huge graph, 2.7 thousand nodes. It does convolution and then nonlinear function, as before, through message passing, first layer. And then you have a second layer, which does a convolution, nonlinear convolution through message passing. And then you have the output, and you look at the output, okay? So there are 2 layers, and 16 is the hidden side of the neural network, so you don't do that. Okay, now I'm importing libraries. Do you remember that yesterday we saw in the message passing, we had the rho function, the gamma function, the sigma function, that we were doing the aggregation, nonlinear transformation. They are multi-layer perceptron. And with a 16 layer, 16 units means that they have 1 layer of 16 units. And you learn all of them end to end. So, okay. This is a plot on 2 dimensions of the labels. Okay, so we know that there are 7 labels. The space is very, very rich. The cardinality is 1.7 thousand. There are techniques which allow you to do a projection to see what you have in 2 dimensions. Okay, that's it. So what you see is that they are scattered around. Each point is a class. Okay. The colors, each color is a class, is a type of document. Say yellow history, blue science. Now, okay, so we already ran, I was just running while I was speaking, and the graph neural network ended the training. So it was a question of a couple of seconds, few seconds. Okay, so we should not think of more monsters in terms of computation, not necessary. And then, okay, first we look at the test accuracy, and the test accuracy is moved to 77% on the test set. So it was a 60 without considering the connection, the topology, it moved to 77. Don't be surprised. Every time you have a problem that has a clear structure in terms of graphs, you will be impressed by the improvement in results. And this is something very, very simple. So I was not doing anything strange. Just play one graph neural networks with some parameters. If you look at the literature, you can do even better. And these are the different methods on this benchmark. And if you play with the graph neural networks operators, diffusion, graph shift operator, and so on, you reach up to 90%. So there is a huge margin of improvement if you start playing with things. But as I was saying yesterday, I like the rule of thumb. I try with very simple graph neural networks, and they seem important. If there is an improvement, then it is worth to spend time and play with operators, layers, otherwise not. Now, I don't know how to go back. Sorry. Probably an ask.
Yeah. Suppose that we look at the graph.
Now I want to show you, let me finish. There is only one picture, and then the other chose this one, yes. Okay, so let's see what the graph neural network is doing in terms of labeling. It takes some time. Okay. So this is what you get when you apply the data set to the graph neural network. And you get the labels. So you see that what happened, it did a transformation of the space, and it was trying to put all the points, related points in a part of the space. Again, the space is 1,700 in dimension. And what we see here is a projection in the 2D space. Okay.
You get the graph. I mean, the graph structure comes from citation.
Correct.
So if I just draw the graph, show the links, just the links. So, I mean, if you said the categories is history and science, for example, I don't expect to find the link. Anyone from history, science, or so if I look at the nodes that are connected, I may end up coming with something that's going to be maybe close to 100.
Yeah, but you see, you're saying that you need to look at connections.
Yes, and I know that we're taking advantage of the structure.
Absolutely, yeah, but listen, that is exactly what the graph neural network is doing. Exactly, is doing that through the proper operators. And nonlinear transformation, because the world is not linear and you want to reshape the manifold. But that is the concept. You say that if you look only at the data per se and the features, you get what you get. But if you look at the fact that there are dependencies, which is, again, as I was saying, a direct graph in this case, then what you get is, I cannot say optimal because there is not the concept of optimality. But what you can say is improved, and you can assess improvement in performance in a statistical way. Okay, so through all the same methods. Okay. So I think that this concludes the second part. If you have questions, happy to. Otherwise, we can move to the third part where we have now time. So not only space. To me, space means we have. I need if we can close this and upload the third file. So time is that we have a graph. We are happy about this. That is space. Whatever it does mean, because not necessarily it is space, but it is, we call it space. And then you have time. So, and what we want to do is to process space in time.
Any questions for this
Yeah.
part?
So the good news is that there are really many libraries, and you don't need to start from scratch, because you can imagine how difficult it is to implement all those architectures. So if you're not an expert in doing that, it is very common making mistakes, bugs, and whatever. So it's better to have something to have understood what is behind, and then you play with things.
I have one question.
Sure, Stelios.
So I want to ask about the computation complexity of the different steps that you mentioned. For example, when you have, let's say, graph with millions of nodes, and you still apply these operations, or is it beyond, let's say, the ability of the This is one question. My second one is what happens in the case where you have features at both the nodes and the edges of the graph? Can we still apply?
Yeah, sure. Okay, so computation. Computation is indeed an issue if the size of the network scales significantly. If you look at what Google and Amazon are doing, they try to retrieve information related to people, any type of information. We are the node of the graph, and the vector is whatever they are able to grab. If we are connected directly or indirectly, so there are people and also companies that sell products. So those are nodes as well, or products are nodes as well of the graph. So everything we are connected. If I use my credit card to buy something, there is a connection, okay? And so you have to imagine that the size can be 1 million. And then what you can do, at first, it depends on the type of problem. So the transductive learning, what we saw before, scales very well. You don't need to do very strange things because it's just convolution, which is something that you define the kernel and you start moving around in your graph. Even if it is very complex, it will take time. But you know, if the value is many million, you use parallel machines, it will take 1 week, it will take 1 day. And what you get is what you are going to use. So these things are not a thought for real time, even if we know that real time doesn't mean anything. So 1 billion year can be real time for the history of the universe. Can be real time, or 1 millisecond might be not enough if you have something that is high frequency in your need. Okay, so computation is there. There are methods which allow you to scale differently. Sometimes you don't need to do the convolution all over the planet. Why? Because simply you don't care. Or people have different habits and attitudes. So if we are in Cyprus, you buy different things from what we do in Italy, or from what you do in India, different needs, cultural necessities, you see. So you can always somehow confine your huge graph in subgraphs. That's all. Okay. The second question was
About the features of the nodes.
okay. Yes. What I was considering here was only related to topology, because of the topology and features associated with nodes. If you remember yesterday, we saw that general message passing also includes features associated with edges, which means that you take the features associated with the nodes, you do an embedding them through a multilinear pattern, and then you do the very same with features associated with the edges. So now you have an abstract representation at the embedded level, which is used by the message passing to update the state of the node. Okay, and then by doing that, you update that. It is part of the message passing. Okay, I think that we have still half an hour before the break. Right? So let's start with spatial temporal graphical networks. So now we have space and time. Sorry. Okay. Yeah. So we will start with graphs and time at first. Then we will focus on sensor networks because we know that we are very much interested in that and not in social networks or the computer systems. So we will say that our graph comes from a sensor. And then we will say, okay, now we have space and time. We understood that how powerful graph neural networks are. How can I integrate the concept of time in the computation? Which means that now we will focus on the locality principle associated with time. If I have a signal and I look at the sample, it is very high the probability that the previous sample and the next sample will be close to myself. And that is the locality principle of time, which will enable us to do convolution and blah, blah. Then we will see that in the real world, there are many challenges. One of those is that I know that you are processing your data and you have a huge amount or a significant amount of missing data. So you acquire data and for any type of reason, not necessarily a fault at the sensor level, you don't get the data. It can be a problem with communication, logger, it can be a problem with your server that was not updating the database, blah, 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 whatever. So you have holes. And what we want to do is to take advantage of the fact that we have dependencies to fill up those data, imputation. Then virtual sensors. So if I'm able to fill up the gaps in my signals, having all those graphs dependencies, and what about if I have a new sensor that I want to buy and I want to put that sensor here? That is a type of imputation where I want to reconstruct the entire signal by knowing that that guy is connected to me. And that is called the virtual sensing. And then a very last comment on a latent graph inference, which means if I don't know the topology of the graph, what can I do? So how can I learn the topology? Either functional, that is easy, or through a distribution, and then we see, okay? So that these are the topics. And then the good news is that at the end of the day, there are libraries which will allow you to implement what you are going to see, okay? Okay, graphs and time dimension, and then again, we focus on systems, okay? But so physical, I'm not going, blah, blah, blah. This is, you know, much better than me. We have interaction networks where you have time. too. So over time, we exchange information. So social networks, recommended system, sensor networks, smart grids, traffic networks, whatever, physical sensors. So how can we model such systems? So there are 3 different modeling for the system generating data information. And depending on what you select, you have a better use of the technology. The easiest one is when you have sensor networks. And clearly, you understand that with the social networks is a bit more difficult. That is intuition, which is also true, which means that you also need to consider different operators or to pay attention to different issues. But let's look at the 3 different setups. So the first one is the graph stream. The graph stream says that if you have a discrete signal, over time, you get one sample. You might be sampling at the very same frequency, but not necessarily. So we will have also cases where, the sampling frequency is not constant. And sometimes we will get one sample associated with some time t. So we are able with graphs to carry out an asynchronous processing. That is very important. But anyway, so in the most general case is the graph stream. Over time, whatever it does mean, you get a graph. You have a stream of graphs. Then we will go into a bit more. Temporal networks. That is a second setup, which is closer to the applications related to interaction networks, to social networks, interaction networks, recommended systems, because you want to interact. So the focus in the temporal networks is on the interaction, on the connection. I'm interacting with you. So I built the connectivity now, and I want to focus on that. The third setup is what is called the spatial temporal graph signal, where basically you have a time series. So you have time series, multivariate, but there is a topology, sensor networks, let's say, and you want to exploit that information. So graph stream. The graph stream is a very general setup. It is very complex, though you can do many things. So the first comment is that you have a stochastic process that is your system model. You need to make some assumption. For instance, you say that the graphs are IID. Or if you have time dependency, they might follow the same distribution, but they might be dependent on time. Depending on the assumptions you make, you need to use the different applications. Okay? So you have a stochastic process, which means that if you have a stochastic process, you have time dependency. So you have these random variables which are dependent to the time, they are dependent, and each of which is generating a graph. Nodes are not identified. So this is the most complex case in graph streams, which means that you generate a graph, but when you look at the nodes, they don't have colors. So I cannot say that this node at time t will be associated to this node at time t plus 1. I don't know. Very complex. You have a structure which comes in some shape, and good luck. That is it. That is what we do with the graph streams. Every random variable, also over time, can provide arbitrary changes in topology. So the topology can change. And well, you can bet that it is difficult to track changes, what is going on there. And it is not trivial to define the concept of statistics, though you can. So you can do something. Okay, so the reference is my PhD student here, where the thesis is addressing this slide, the comments. Second, temporal networks. Again, the focus now is on interactions. We want to interact. That is what I'm interested in. Recommended system. If I'm going to say, to provide you, look at this. So I'm interacting with you. Will you happy? Will you be happy? If I'm giving you this, proposing you to buy this item, will you be interested in that? So the focus is on the interaction. And a good reference for this type of problems, you see here, you have the different nodes and the focus is on the interaction, which might change with time. And that is the focus. So the system model is now pushing on that. So what do we have? Relationship evolve with time. Most of times the graph is identified in the sense that I can say that it is you. And if you're using a different computer, but you have a Google account, it is still you. I know it is you, okay? Even if I'm Nicosia, it is me, because I connected through my Google account. You see? So interaction is the focus, but nodes are mostly identified. So we know that it is me. This is very effective for social interaction networks and the recommended system. This one is a very good reference. So if you have problems that can be cast within this framework, that is it. The third one, which is the one I'm going to focus in, given the KIOS, is the spatial temporal graph sequence. What does it mean? It means that when we look at what we have a time series. We have a set of sensors, V0, V0, V4 in this case, each of which is providing a signal. It will be a time series, I should say, discrete samples. Okay? They might come with the same frequency, different frequencies, but it's not a problem. We will be able to process items coming at different frequencies. If we look at this, so we have a multivariate time series, we have sensors. When I mean a sensor, I'm saying that I'm collapsing a sensor with a one signal, which means a time series, which means one channel. If your sensor has three channels, like in a gyroscope, for instance, or an accelerometer, okay, then I consider them to be three sensors. And they will be dependent. So there is a subgraph, okay? But just to understand. So for me, a sensor is just one entity that is producing a time series. Edges describe functional dependencies. What does it mean? If we have a series, they might be somehow related. The relation we are interested in is functional. Then, if it is also physical, so I'm physically connected to you, fine, but the functional dependency is more important, more relevant. If I have a chain, it means that the physical dependency is affecting the functional dependency. But sometimes we might have sensors that don't have any physical dependency. I don't know. I have a temperature sensor here and an accelerometer or a strain gauge up there. Different sensors. Do they have a physical connection? No way. Do they have a functional dependency? The answer is absolutely yes. Why? Because if you look at the strain gauge, you know that the temperature will affect the readout. So variation in temperature will change the readout from the sensor. That's why we do the compensation, thermal compensation, in offset and gain. But if we don't compensate, those two sensors, which are looking at different planets, are related. Okay? And that is the functional dependency. Functional dependencies is also associated with causality, physical constraints, but the functional dependency is more than that. Okay, so it is something that is embracing everything of those aspects. Indeed, the sensors, the underlying graph can change with time. So everything can change with time. So we will focus on this. And I will assume that the process is stationary, say, time invariant. Okay, special temporal graph signals. So what do we have is always the same story, a set of nodes. Now we have a sense of network, it's very clear. They have a name, and so it is an identified process. We know that that is sensor number 1, and it will be always sensor number 1. The nodes, the sensor, will define what we call the space dimension, even if it's not related to space, but they are scattered around, that's why space. So it means the graph. And sensors are related according to some measure of similarity, which what we will see at the end. But again, two signals, Pearson correlation. If you have a Pearson correlation, they are linearly correlated. It means they are correlated. Granger causality. If you like something more complex, use a Granger causality. Okay, so you don't know that, you can learn the adjacency matrix, which is the final case. Again, the elements we have. So we know that we have a graph. The graph is characterized by the adjacency matrix, which depends on time. It depends on the graph signal, so the features associated with the sensor in the matrix capital X, as I mentioned before. We have the features associated with the edges, capital E. And then we might have also extra variables. We call them variables. It means that there are some extra information which are not related to your problem. You want, for instance, to predict, I don't know, the temperature of this room, but you know the weather forecast. And so there are other features which come, other data that you have, and they might be related somehow to your problem. And those are the, why I'm saying this, because if it is going to be very hot outside, then the air conditioning will try to react, but it will take time. So it will affect the temperature here. You see, this is the dominant effect. But they are not part of what you are mainly interested in. But they are there. And you might wonder to see whether by using them, you can improve over you. Okay, with this notation from T to T plus capital T, it means that we are considering an interval of values. So from here to here, okay? A snapshot of your signal, or a snapshot of your graph stream. Okay. So let's again try to get the picture of what we have. So we have sensors. They are identified, which means they have a color, sensor number 1, sensor number 5. They generate over time a time series. But we have more than this. I'm telling you that if we take these data and we put them in a vector matrix, because that is my file, you know, what we get is the graph signal, is the data we have, my multivariate time series. But we have also the adjacency matrix. We know they are connected. Again, Pearson correlation. So, and the topology is this one. We want to keep it constant over time. That is fine. That is the topology. So we have more than the data per se. We have also the graph, the topology. And now, if we blend these two items, it means that over time, we have a graph whose values will depend on the signal. So how should we intend this graph stream? It means at a, let's look at this one. At a time t, each sensor is generating a vector, which is the readout of the sensor at that time. If my sensor is a camera, I take a picture at time t. That is the information associated with the node. If I'm a temperature sensor, at time t and the node, I take 1 second. Okay? If I'm an accelerometer, at the time t, I have 3 channels, I take 3 samples for the 3 axes. Okay? That is what we have here. And which means that if a time passes, evolves, you will have different graphs. If you don't get anything from one sense, because maybe it is off, it means that that node will disappear at that instant of time. Okay? We will keep the topology fixed only for convenience, but it's not needed. So I'm saying that if the node is disappearing because it is not, there is not a value coming from the sensor, that node, the graph degenerate, less nodes. And also the connections will disappear because there is no more connection. And then they might reappear later on in the future, okay? But that is their life, so that is fine. So, but the topology is fixed. So we were able to learn the topology somehow at the beginning. We are dependent in this way, and they keep it that fixed. Otherwise, also the topology can change with time, and we do that, but that will be further more complex. In process or networks. Okay. So then I think that we might take a break. The role of the adjacency matrix. Well, we always said that it is modeling the topology. Now, it is more than that. Because if we look at the graph and the connections in terms of functional dependencies, it means that the topology matrix is reducing the degrees of freedom of your graph. If I'm alone, I'm not connected to anyone, I can do whatever I wish. I have all my degrees of freedom. But if we are connected, whatever I do will influence Thomas, and whatever Thomas is doing will influence me. Otherwise, we are not connected. That is somehow reducing the degrees of freedom of the system composed by the two of us. That is very important. Like in a compound, a chemical compound, you have the atoms, but if you have the chemical bonds, they cannot do whatever they want, those atoms. They are connected together. You can give more energy to the oxygen, and it will start jumping around, moving around. But it cannot go out unless you put much more energy. So your system is reducing the degrees of freedom. And that is the key point which provides all the value to the forecasting, to the imputation. So yes, it is true that I don't have you. but we were dependent previously. So can we use all together to try to infer what you are doing, even if you are not providing the value? That is imputation. Okay. The fact that we are dependent means that it is reducing the degrees of freedom, but it is positive if we want to do process. So let's take a break, and then we will go back and elaborate on this. Okay, so we are back after the COVID break for this very last part of this lecture, these seminars. Okay, so space and time, graphs, space, and evolution of the graph over time. Sensor networks, that is the type of applications we have in mind when we talk about the spatial temporal graphs. Assumptions, we assume the process to be stationary and invariant, we assume the graph to be homogeneous only for convenience, which means that all the sensors associated with different nodes are always on the same time. So that we produce vectors, but all channels will be the same. If some nodes, that this is very simple to resonance assumption, it is not even an assumption. But if I make this assumption, it will be easier to look at limitations and so on. Otherwise, if that is not the case, you have a vector where inside you have the result coming from the sensor you have. If you don't have a sensor because it is not mounted, you will have always a sensor. It's very simple to say, I don't have a sensor. And we assume to have a known graph, so the topology, the function topology is clear. If that is not the case, we will see how to learn. And it is fixed. It is not going to evolve with time, and we can address, however, keys that also the topology changes possibly at every single time step through some distributions. Okay, so now I touch it. What am I doing? Okay. So spatial temporal graph neural networks. What we want to do is at the end of the day to build the predictors. That is my request. If then you want to use predictors within a control framework, that is up to you. So the idea is that we are very much interested in this framework to predict the next values of the time series. So they are multivariate, and we want to know what is going to happen in the future, given the fact that we know the topology. That is very important. So the next values, what is going to happen tomorrow with a forecast, whatever. So basically, if we put everything into a function, what we would like to do is to build some family of models, parameter f, parameterized in a vector of parameters theta, that is my predictive model, which receives a time window of the graphs. So like in Armax models, they are linear time invariant models, so you receive a time window of the past and you want to infer the future. And the future for us is the x hat related to some interval. I'm interested very much in predicting the next future time series within a time interval between t and t plus h in the future, from tomorrow morning until tomorrow evening. So that is my goal. By processing the graph stream that I was able to generate from my multivariate time series. Okay, so It is more simple than it might appear. So if we have time, do we know how to process time with machine learning? Sure. Either you use traditional techniques. If they are there, why should not we use them? Or if you prefer machine learning techniques, you use with time recurrent neural networks. Use LSTMs. You have time. Temporal convolutional neural networks. You do convolution over time. Or transformers. You take time and time series and you do whatever is needed. You know, we know already how to deal with time. And if we have a space, the spatial dimension, well, we know how to process that. If there are images, convolutional neural networks. If there are graphs, because we were starting with there, and then we moved into the graphs, graph neural networks. So we are able to process space and time. Then the fact that you use the transformer or the recurrent neural network, I really don't care. It is just the function, part of the function f you're going to put here. So the point is, how do we blend, how do we treat time and space, having a graph? Okay, so let's again look at the picture. We have our multivariate time series. Each row is a signal, is a discrete signal. And we have these capital N sensors. So we have this matrix, which is the graph signals. Then we have the topology, because that is what we really have, functional dependencies. We have a crunching machine, taking all the data based on some models, processing time and space, and predicting what is going to happen for this signal in the future for a time domain. Okay. We will consider family of models here that will exploit message passing. Why? Because message passing is very general. It is able to deal with features associated with nodes, edges, changes in topology. And then we need also to play with the graph shift operator. You remember the graph shift operator was starting from the adjacency matrix, and it was taking care about what is going to happen, one step, one hop from me, two hops, and so on. So everything will be mixed somehow in a cute way. So if we look at message passing, we have time and space. What we have to do is very simple. Conceptual. So, well, you know, message passing has this notation. We take the message coming from node I. We take the message, we build the message feed by processing features associated with the node I and that of the node J, I crystals. And then the features associated with the edge between the two of us. We build a message feed. I'm node I do aggregation. I receive a message from Stelios, one from Dimitri, one from KIOS, one Marius. I do aggregation. By looking at my neighborhood, I'm node I. Around me, there is the neighborhood. And then that is what I do. And then I update my state with respect to the information I had already, in addition to what I received from the message. And then I process everything with a nonlinear function. The output is my new state, if we want to look in this perspective. That wasn't message passing. But now we have time too. That's so difficult now. It is already in this equation. So it means that message passing, look at it, we have a kind of window. So we use the past values of node I, the past values of J's, the past values of the features associated with the edges. They are vectors, matrices, tensors. And they evolve with time too. Okay, put that everything together. Crunch this data in time. Through P, you aggregate, and then you process everything, you join, you blend everything together through function gamma by looking at my time history. Not only a sample, but what happened to me in terms of features in the past, W samples. Okay? And what you get is my new state. Functions phi, gamma are regular functions, actually percentage, which will be whatever. And but maybe not, in the sense that if we needed to process time here, you see, we need to process time in the message. Time, we need to use the recurrent neural networks, transformers, time convolution neural networks, you see? So that phi can be a multi-layer perceptron, but maybe not. So now we go into this details. So again, this phi is the message function, aggregate is the negation function, gamma is the update function, and we need to pay attention to the fact that time is infinite, but conceptually nothing changed. Okay? Now, locality principle, that is our inductive bias. We have a locality in space. So given one node, is very high the probability that the nodes connected to me are connected to me. Of course, they are connected. If I'm getting further away, there is still the probability that we have some indirect relationships. Again, locality in space, and then locality in time. If I'm in the sample, it is a high probability that the previous sample and the next samples will be dependent somehow. So locality principles, convolutions. How do we do that? There are 4 ways to process and generate the graph, which are intuitive in a way. And the last one is not. But let's have it. Time and space. If we have a time and a space, I do convolution over time, then a convolution over space, correct? Time and space. So time then space. Or the second one, space then time. Convolution over space, the graph, and then you do convolution over time. Clearly, you are changing the operators, because if you do convolution over space, graph neural networks. If you do convolution over time, the current neural networks, transformers, other technologies, okay? And what about if we do time and space processing all together? And that is time and space. Then there is another approach, which is called the product graph, which starts from space and time, and will generate one graph. Only one graph, which is the product graph. And having this unique graph blending space and time, you will do all processing there. I will go into the further details. But as you see, some of them are very intuitive. So time, then space. What I was telling you before when I said we know how to process time, classical techniques, means that we should use those technologies to process time. And then when you move into processing space, use graph neural networks, because that is the technology that we have today. It can be with attention, self-attention, whatever, but that is the technology. So time, then space. At first, you process time. Okay, so here we have our signal again. I call it again signal, but it means a portion of a time series, time window, discrete signal. It's not a continuous. So each one is a signal, and we treat each of those signals coming from sensors with the same machine. For instance, sequential encoder, a recurrent neural network, a state space. So you receive your data and you generate the state value. You do a transformation. Okay, and it is a recurrent. Think of state space models, linear. New data, you generate a state, and then this state will be now, which means it is a vector, will be blended over the graph topology. And then you have space, and you process space with a graph neural networks, deep if needed. Okay, time and space. But again, the key point is that you take a signal, you have a recurrent neural network, if it is a nonlinear or a time state space representation, the data, you crunch it, you have the state, you use that. And then we know that that signal was associated with a node, which means that the state value will be the value associated with the node. And it will be mounted on the topology, which means I process this one in a recurrent way. I get one value in time, which goes in. I do the second one, I get this one. And then we put everything in the topology. Now we have a graph, and then we process space through a graph neural network, message passing. We start moving around, and the outcome will be the forecast of the value. So when you look after this message passing, the value of myself updated, that will be the forecasted value. Okay, is that clear? Very simple, very neat. You train everything end to end. What does it mean? It means that, let's say, assume here we have a recurrent neural networks. They can be the same recurrent neural network, or they can be different. And you need to train all these parameters. And then you have the graph neural networks. You need to train all the multi-layer perceptron in there. The gamma, the sigma function there in there. The rho function, if you have the rho function. Well, do you need to do a prediction? Okay, this is my time series input vectors, and this is the output, which is a vector. You train the loss function as you do it with any predictive model. You like, I don't know, maximum likelihood, you use maximum likelihood. You like mean square error, use mean square error. Frankly, I don't care. You train everything, and by doing that, together, you train this architecture and this architecture, all together. Okay? Okay. Space, then time. In space, then time means that you were starting with the multivariate time series, and for at every single time instant, you had a graph. And then you have a graph stream, different times, different graphs. You have now a sequence of graphs. You need to process space at first. So graph neural networks. Separate filters, whatever is needed. And the outcome is going to be a time window of what is going to be predicted. But in reality, this one is just processing space. Now you take these latent representations, representation if you wish, and then you apply convolution over time. Recurrent networks, for instance. Linear ARMA models. And then you get the forecasted values.
So here we are assuming that the network is changing, whereas in the previous the network was fixed.
The topology is fixed. I'm assuming that the topology is fixed.
So here,
but the topology, but it doesn't mean. So if I look, sorry. The topology fixed means that the adjacency matrix is full, but you might have cases where the information coming from the node is not there, which conceptually means that the node is disappearing. In reality, it means that you put a value 0 or not a number, and then you, or infinity, and then you treat in a proper way, you ignore what is in there, okay? But the structure is fixed. So, which means that over time, you might not have the features, because when you look at these colors, they have a number in there, or a vector in there. If it is not existing, it means that that vector will degenerate in either 0 or a none or a infinity. To say that you should not consider that, which conceptually means that the node is disappearing. Okay? Right. So space, then time. And within these architectures, when you look at this, not rarely what you do convolution over space, convolution over time, convolution over space, convolution over time, or convolution over space and then convolution over time. You decouple that. The good thing about space and time, that you decouple convolution of space and time, that is that you reuse whatever we have. You don't need to implement something new. You are reusing recurrent neural networks, you are reusing your graph neural networks as they are. So that is a plus. The problem is that you might tell me, yes, but I don't like to have at first to process space and then time, because I'm implicitly making assumptions about the changes over space and changes over time. So if I don't want to do that, I needed to intervene at the operator level. And that is what a time and space is. In a time and space, you design new operators always belonging to the family of a message passing. So you redefine the operator belonging to the same family, trying to play with that. So one possibility, and we will look at two strategies, is to interleave space and time. I do one convolution over space, one convolution over time. I don't go deep. One space, one time, one space, one time, one space. That is one possibility. Or we use graph-based recurrent neural networks. Wow, what does it mean? That we have a recurrent architecture where the input is a graph. So you go inside in this recurrent architecture with a graph, you get a graph, the graph goes back, is fed back into the recurrency. And then you process space and time. You see, it's not a vector going inside, like in a state space model, in a traditional ones, but it is a graph going inside. You have recurrence, you have the previous graph, it is recurrent, the output is a graph, and you process that. Okay, so let's see how we can do that. So one possibility is to alternate space and time convolutions. It's very easy, so very natural. So what does it mean? At first, we do convolution is a star over time. Okay, we get some value. And then we do convolution over space. If you remember, convolution over space means to use a graph neural net. And this is the equation of a graph neural net, where you have the graph shift operator, the adjacency matrix. Here you have what is coming from the previous convolution over time, and then you have the local parameters, and you get the new representation. That is what you do. If you put everything together with an abuse of notation, but just to get the idea of what in reality we are doing the convolution over time here, you see, a nonlinear convolution, and then you apply space through the graph shift operator and the parameter filters, theta 2, and then you get a new representation. That is what you do. So you blend everything together. Right. Another possibility to blend everything together is to do something like this. Now, apart from the equations, it's just to understand what we are doing. So, and then let's start from the second one. So it is message passing. Message passing means that we needed to build a message, aggregate the messages, update my state. The message is doing a temporal convolution, time convolution neural network. So it is doing the convolution. Then you have the aggregation, the message passing, and then you have the temporal convolution network. But this one is the graph. So it is again the same from a different perspective. If you look at the implementation of what you say, is a bit more complex, but it goes into details to see what we do in reality. So what we do, so this one is convolution over time, you see this tau. And here is the vector that goes through the filters. The vector says you need to take a time window of the signal of node I. You make a juxtaposition. So this one will be either a matrix or a vector. You make a juxtaposition, so you append all the information of a time window associated with the node J. Then you append juxtaposition all the information over time that you get from features associated with edges. So you take everything together, one after the other, a long, huge vector, and you do convolution over that stuff. Through these parameters, which are theta 2. These parameters is not only one mask, one kernel, but are a set of kernels, like in a CNN. What is coming up is aggregated, is a message. So this message needs to be aggregated. And what you get goes through a juxtaposition, goes appending to my information. Okay, so I'm processing I'm keeping all the data. I do the whole convolution, I aggregate, and then I don't compress, if you wish, all that information in one number, in one vector. No, I keep it. Finally, what I get is a huge vector, and the update goes through space, and this is me. Another convolution over space. And the space means the graph. And then you update this my state, which means the state of every single node. Graph, the graph, space, and time now are blending together in this. And this is an example of the implementation where you put everything. I'm not going into the details. I'm just telling you that there are many architectures that do this in a proper way, depending on some principle or some assumptions or on some ideas, flavors, feeling you have about your application. So basically you see here is a deep architecture. You have a convolution over time. It is gated, which means that you have a gated recurrent units in there. Then you do convolution over space, which means a graph neural network, which is telling you the parameters, and then it goes again back to the convolution over time. And this is the building block. Would you like to have more modules, deep layer of that? You stack one after the other. Or you have something like this. So the key point is that, apart from the architectures, is that you have a time convolution. You see here, time convolution, you make a convolution of time. You have a graph and neural network, which means convolutional space. You have some gates inside, like in long short-term memories, like in gated recurrent units, because you want to have something which is changing over time, and those at the same time you want to keep short and long dynamics within the same setup, with the same thing. So I'm not going into details. There are references, very good papers. You will find the architectures. It is very nice. So I was commenting about GRUs, so gated recurrent units. I don't know if you are familiar with them. So the idea is that if you needed to design the neural cell, the basic cell, it's not enough to say the recurrent goes input, state, previous state, and back. No, inside you have a bit more complex stuff, which says that you have some gates, and these gates will try to balance the contribution of the input, previous state, forgetting state, so you want to forget within the unit or your past memory, and you want to blend all these contributions in order to generate the new state. So the new state is not only a linear, simple combination, a sum of what we have, but the gates are controlling them, so that if it is needed, you will discard all the dynamics. And you do this with long short LSTM, long short time memories, LSTM, but they have 3 gates to be controlled, which is a lot. And so GRUs, they just need 2 gates in order to control the inner dynamics. Yeah, very powerful. Indeed, if you want to process time with dynamics which can be different, fast and slow together, you need to consider this. You need to balance what you forget in order to generate the new state. So these are just the equations. It's not going through the equations, but just the flavor, what is going on. And this is time. And now you might ask, and how can we integrate a convolution with respect to space, the graph? Well, this is another way. So this is very useful in a traffic forecasting context. So, I mean, I would rather say in any application. The good point is that if you want to control those gates, you can do that through a graph. So the output of the graph is controlling the gates of your units. And that is how you blend and you put space into this architecture. So there are many ways to solve that, and some of them are very intelligent. I'm not going into details, but an example, I want to show this one. Okay, this one is, again, with GRU. What does it mean? That these are the elements which are the state of the cell, the state of the previous value, the values associated with the 2 gates. They are a function of graph neural networks, you see. Sigma are nonlinear function, multilayer perceptrons. You have the previous state and the graph, the very same with the U. Then again, you have some linearities. And but what I want to show you, apart from this formulation, is that you have all the parameters that you need to learn. And again, you learn the GNNs, the sigmas, whatever is in there, end to end. You put the architecture, you have time series, predicted value, you want to minimize the forecasted error, creating the set. Here in the bottom, you have the equations where when the graph is directed. When the graph is directed, it means that in my topology matrix, in the adjacency matrix, we have, and I know that there are connections to me and connections coming out from me. So I receive information from some of you, and my output goes to some of you. There is direction, there is causality, okay? When you do this type of processing, you need to process in a different way with different kernels what you receive in from what you release out. So they collapse when you have a bidirection architecture graph. But if you have the time arrow, if you have arrows, so you have, inducing something, so there is an arrow in my edge, you need to split it. So what you see here, this one is a random walk, this one is a graph shift operator at a power k, which means that I'm going not only look at my neighbors, but 2 hop neighbors or 3 hop neighbors for what is coming out from me, and in this case is from what goes in. So you can train in and out different. Okay, product graph. So clearly, I don't go into the very fine details of the method. It's just to get a glimpse of what you can do and the overall picture. But you can do really many things, and as we have seen, you can treat in the proper way situation where you have a directed graph. So the product graph is very interesting. So you have a time passes, and you have space, the graph, the topology. You need to put everything together. So, and what you want to do, you take a product of the time dimension with the space dimension in order to build only one graph. One possibility is to say, okay, space is this graph in orange, this graph in orange, this graph in orange. Time is just connecting the element, the sensor, in one direction, because the times moves from t to t plus 1. If you don't have a t plus 1, you have a t plus 2, it means that you jump, and it will go to the next value. So this is time in blue. This one is a time t, this one is time t plus 1, this one is t plus 2. But then at the end of the day, I look at this as a unique graph. This one is the Cartesian product. The other one is the Kronecker product. Basically, each node, this one, is connected only, that is the point, to its neighbors in the previous time instant. So this one was connected to these values in the previous time instant, and this is the graph. The final graph you get is this one. You might say, oh, autistics, that's very crazy. Now, I show you an application that will be clear what you want to do. Look at here. It is an input video. You have frames, and what you want to do is to detect what the lady, in this case, is doing. So you want to classify, is she running? You might even think of trying to predict the speed of the run, the velocity. You have a frames, you skeletonize, that is the graph, the person, what you have in the scene, and and then you build the product graph. You see, they are all together. You have a huge graph. And if you take a time t, you cut it, you have one skeleton of the scene. When, look at here, we do convolution in space and time. Basically, what you do in this point is processing locally what the elbow is doing. If you look at this one, it is processing the evolution of my leg over time. And then finally, so we know that this goes through the GNNs, because now you have a huge graph. So you do graph neural networks in order to make the final assessment. And then you have, if needed, in final multi-layer perception, which is going to provide the output of the class score. What is happening inside? You see? That is a different way. But if you look at this case of this application, you understand neatly why you want to do that. Is that clear? Okay. Challenges. And in the challenges, I want to comment and provide some hints about imputation. What is going to happen if we have a missing data? First example. What about if I put a sensor here, which is related in space, we know that, and we want to infer what it's doing? All these things. Okay, so space-time graph neural networks are very powerful tool. Indeed, you can solve many problems, but what about if you have missing data? If you have missing data, you start making assumptions about the process generating the data. You make assumptions about the number of missing data, the occurrence. So how many failures I might have over time, probability. So you build assumptions, and then you come back with the methods. If you have a topology, if you have a dependency in space and time, that, as I was saying, that is a very strong constraint. So my sensor cannot do whatever he wants if it is related to your sensor. They are reducing the degrees of freedom. So if I'm not able to provide a value, the others will help me to infer what I'm doing. So this one is called imputation, which means reconstruction of a missing data. There are many techniques. We have been working with the Christos and Marios within iSense project on these things, but having a dependency, having a graph results are further much better. Okay. So in a traditional approach, what you do? So you have time, you have the channels, your sensors. The blue elements means that you have the value, so they are ready. The red means they are missing. Clearly, if you look at this picture, you say, well, we were making assumptions. If a signal has one single missing data, then you can build, I don't know, a linear model or whatever. If there are more than in a sequence, you need a mile. So you need to build and make assumptions and build a solution, linear, nonlinear. But if that is what we do, so we were doing forecast and we were filling the gaps in imputation with these green estimated missing values under some assumptions. The approach was basically the formalization of this one. So you start from a time series, which is this one. And what you want to do is to provide a value for the missing values following some probability distribution, which is unknown, which is conditioned on your time series. So this one is unknown, and what you want to do is to find the best estimate. You need to learn the probability or to take expectation. That is another possibility. But we were able to do that. So this is the problem. We start from the data, and we want to infer the probability. Very complex. So within a graph approach, what you do is to take advantage of the presence of the topology, the links, the constraints. And if we look at the formalization of the problem, we move from a setup where you start from the time series and you want to learn the probability for inferring the missing data or the data that you have, into a problem where starting from the data and the evolution of the adjacency matrix over time, so you have the topology that can change with time, even if we assume that it was fixed, but it can change with time. We want to infer the missing data or the next data. So the problem is different. We take into account explicitly the adjacency matrix, and we want to use that to improve the I just want to present to you one method for doing this. It's called green. It is a graph recurrent imputation method. So the idea is the following. We have our data with the missing values in there, but we have the topology. And what we do, we need to do convolution over space. And every time we do convolution over space, if something is missing, I can make an estimator for that. That is the key point with a graph neural net. Then we need to exploit time. But when we exploit time, we know that we need to use something recurrent because there is a dependency that depending on the dynamics of my process. And that is something recurrent. So within this framework, we have something like this. You have time series coming inside. They are transforming into graphs. And then you have a recurrent machine that is receiving a graph, generating the graph, the next graph, and then it is recurrent, the previous graph goes back. On the top of that, we look at the problem, and let me go back. So here, from two ways. So if we do imputation, it means that our data are in a file. They are there. They are not coming. This is not an online reconstruction. In an online reconstruction, data come, you have a missing data, you have the topology, you build the prediction, which means that you elaborate in space and time, and you fill up with this. You do forecasting of the missing data. But if the data are in a file, what you can do is to look at the time as if it were reversible. What does it mean? It means that if these are my data, I can look at the time arrow from left to right. And every time I have a red point, I make an estimate. But I have all the data. So I can start from the right and roll back time. So I look backward and provide the predictors taking into advantage the topology going backward. And then you harmonize, if you wish. And you harmonize the two estimates in order to improve the feeling. You can, if you use a Kalman filter, you get even better. But this method is not using the Kalman filter. It's just looking at this, taking into account the topology, two estimates, and then you blend them in the proper way. That is green. So what you have a convolution of a space and time, left to right, this one. Then your goal is to generate the missing data. Okay, so this one is, so this line is doing the prediction with time left to right. This one, time is reversed, right to left. And then you have an harmonization stage, which is taking the estimates and blends them in a nonlinear way to generate the final estimate. As I said, if you use Kalman, that is something, so we didn't do it in this paper, but this is something you do. And let's look at what is inside. So you have, let's look at this. You start, you do an encoding. Encoding means that we start by processing time. You take the dynamics, you encode them. Recurrent neural network. So we are able to process time, you make an embedding. With a recurrent neural network, with a linear filter, whatever you want. And that is what you get is the first level of imputation, which means that this recurrent architecture will make an estimate of the missing value. You put a 0, and then it will provide something. And then you do computation over space, message passing. So you take all what you get, those embedded values, you do message passing, and you generate the second level of imputation, the second level of the estimate. You do that with this time arrow, with backward time arrow, and then material per second to harmonize. End to end, you learn this architecture, and the materials. It is a deep architecture, you learn everything, and you will get the estimates. These methods are very impressive in terms of the reconstruction ability. They can reconstruct up to 70–80% of missing data, provided that there is a structure in the topology. That is clear. And it depends also on the nature, the graph associated with the topology. The higher the connection degree for a node, the better the ability to reconstruct that. That is coming from for granted. Okay, so on the top of that, I was not commenting this, but this graph architecture is recurrent in the sense that, so we do convolution over time, embedding. Then we do graph convolution space. And then you make an estimate. But this value, this graph is fed back. So also the graph is fed back within this architecture. So it's a fully dynamic. Anyway, now this is imputation. So if you have that problem, there are very, very amazing, nice solutions to the problem by taking into account these dependencies, functional dependencies. Another point is that of virtual sensors. So, okay, I have my sensors. What if I'm putting my sensor there? Okay. You might have some information which is related to the position in time and space, and which means that your program is partially observable. You can acquire some information, or maybe you say, no, it is going to be there, but these are the connections. So you are saying this. So what is going to happen? Well, I mean, if you know that something is connected, and it is you, and I don't know my values, but I know I'm connected. So the others will help me in providing values. It is like filling up the gaps. But now the gap is the entire signal. And the assumption that you're making is that it was correlated with the others. So if we want to look at the temperature in this room, and I put a temperature sensor there, which is virtual, it's not there, we are able to infer what would be the value if the physical sensor was in there. What you can imagine and what you can get is really amazing. So these are two examples of virtual sensors for the PM2.5. Those are benchmarks. Okay, so let's try to imagine that we don't have that sensor. We want to guess it. Okay, so the truth, so the real value is the blue one and the one reconstructed through the green, so the method I was presenting before, is in the green signal. This is for one node, this is for another. So those are virtual sensors. What you can get is very important. And clearly, if you have information related to space and time, because, to space, because you know it will be there, which means a very strong dependency in terms of distances, then you will get a really very good values. This is important for a what-if analysis. What about if I'm going to put a sensor there? Will that provide clearly? I mean, what you get is an estimate. And the better the connections, the functional dependency, the better results. As simple as that. Okay, now the last point, which is related how to obtain the adjacency matrix if we don't have the adjacency matrix. So we have one of these sensors, we have the time series. We would like to build the time dependent or time invariant adjacency matrix. So let's see some methods. Some are very intuitive. I already anticipated that. But the point is that we start from the multivariate time series, from the signals, and we do a graph extraction. And what you do, you generate a graph with the topology. Okay. Very simple approach, already commented that. If we have time, Pearson correlation, trivial. If there is a linear dependency and it is there, you can also test statistically if it is there or not. You build a connection. Then if it is not linear, who cares? But it is at least linear. You see the point? Would you like to put something associated with the edge? You might say the Pearson coefficient. Does it change over time? Well, you have the topology where the attribute is the Pearson coefficient and can change with time. Take a time window, one Pearson coefficient, time window, another one. You don't like the Pearson coefficient, you just keep the connection. Or Granger causality, that is much stronger. And by looking at the Granger causality, which means the ability from one signal to infer, reconstruct the other, having part of the other one, is much stronger. There are also some very nice statistics associated with this method, which will tell you whether the connection is statistically plausible or not. If it is not statistically plausible, you throw it away because you want the graph to be sparse on one way, and you would like the graph to be dense if it doesn't make sense. Or you don't know anything and you want to learn the graph. So I'm not going to use traditional signal processing techniques, no Pearson, no Granger, no priors, because I don't have the priors, but by feeling something is in there. And I really would like to be able to learn the adjacency matrix. So this is known in the literature as a graph learning or latent graph inference. There are two major approaches, then there are some others, but let's focus on these ones. So the first one says, but we want to learn one adjacency matrix, one. And the other one says, well, the adjacency matrix in the reality is random variable. So over time can change. There is noise in my data. So yeah, you are asking for one adjacency matrix. It's not better if we are able to learn the distribution associated with the generation of the adjacency matrix. So we want to learn a parameterized probability that will induce the adjacency matrix. The second problem is more complex than the previous one. And like in forecasting. In forecasting, I say this one is the expected value. So it is a point-wise estimation. And the second one is say, no, I'm not only interested in point-wise estimation, I want the distribution of the output. And then it is up to me to decide which is the correct one, okay? It is the very same concept. This is a very complex problem, as you can imagine. There are ways to deal with that with the pros and cons. So let's see some methods. One possibility is to say, this will start from this equation, that the adjacency matrix is a nonlinear transformation of something which depends on the information coming to me and what I'm giving to the others. So if there is a dependency between a group of you and me, it means that an unknown group of you is sending something, is connecting with me. And you are the senders. So what I get from you is a matrix. So you send me some information. Then I'm broadcasting my information to you all. But only a subset of you in reality is connected with me, but I don't know. That information goes into this other receiver R matrix. So you do the embeddings of the features associated with the nodes. You put them into this matrix. You apply nonlinear function and you claim that the balance between what I send and what I receive defines the connections. And you learn these matrices. What you get, though, is a topology matrix, which on the average is very dense. So being very dense, that is a plus, but is also a minus, because you generate also some spurious effects, and you don't want that. So one possibility, if differently you want, either there is a connection or the connection is not there, is to control the distribution of the adjacency matrix. And you say, for instance, that the adjacency matrix has to be binary. So it has to have either 0 or 1, either there is the connection or not. And this adjacency matrix follows a distribution, which is a Boolean, so you want the binary values in there, whose expected value, though, depends on the information exchange between the nodes. So what we exchange will contribute to define the expected value of the Bernoullian random variable, which needs to be learned. What is the problem? So everything is neat and do that. And it is also very effective. The key point is that we need to learn this distribution. Let me go here. Sorry. Okay. So basically, what we want to do is to do something. So we say that what we want to get follows the distribution. And the loss function is this one. So what you will get is the expected value taken with respect to the topology matrix of the loss function. So end-to-end, you imagine to build the predictor. You take expectation with respect to the space of the adjacency matrix. You want to find the adjacency matrix that is minimizing this expected loss. And that is what you get. So, but this is an end-to-end learning problem where basically you need to do gradient descent over this loss function. The key point is that you need to take expectation with respect to a distribution, which will be part of the expected value. And it is very difficult. In order to solve that, you needed to use what is called a reparametrization trick. So you change the problem into another problem and you make the process differential. Another way to do that is to take this equation and change that into what is called a score function. So there are some computations you can do. You can place that function, that problem, optimization problem, into an equivalent one when you basically use a Monte Carlo in order to solve it. And these methods are very effective and they do provide an adjacency matrix which follows, and it is the best estimate you can get given these assumptions. And okay, so the good news, as I was saying, is that there are all the libraries. I always had problems with this. So there is also a demo. I don't know if it is worth it to see the demo. So in the demo, what you see is a lot of code. So if you go here, it's going to go. So there are the libraries, as I was saying before, dealing with the space and time. So you can do all these things. In this case, this application refers to the ability of predicting the traffic flow in a city. So that is another benchmark. You do convolution over space and time. And at the end of the day, what you see is the ability, the prediction accuracy. I'm not doing that. I mean, there is nothing special in doing this exercise, but I just wanted to show this to you because if you're interested in this, this is a very nice example where everything is detailed. So there are the comments, we do this, we do that. So the code is well explained, and you see all the steps leading to the final forecast. But you guess that the intuition is that we use space and time convolution. So inside you have, apart from a lot of things, you upload what is needed. There are ways to control the kernels. And then you do convolution in space and time. Whatever, I think that from what I said, this is very natural, and we won't see anything effective if not a number. So I don't think it is worth to do this exercise, but we wanted you to see that because if you want to implement and trial something, if you have something different, you simply change the file that you need to upload. And that is something already comprehensive. Okay? So I think that we can stop it here. If you have questions, I'm more than happy to answer. But the key point, to sum up, is that having an inductive bias is fundamental. So if you have that, do use it. If we know that the model is linear, that is an inductive bias. Call it assumption if you wish. Why should we use something which is not linear? That is important. If we know that there are dependencies, why should we ask the inference engine in something which is so complex to be able to find the right path? It won't be able to do that. So if we can guide the process of the inference engine by making explicit the dependencies, so much the better. So nowadays people talk about a physically informed neural networks, the very same concept in a way. So we know that there is some physics, the mass, the energy, they must be preserved. There are some equations that your system has to satisfy. Those are constraints. that is the inductive bias. Okay, and if you put the inductive bias into the crunching machine, you will get much better than not forgetting that. Okay, so that is the spirit. Let's go ahead.
Yes, I have a question regarding the homogeneity assumption. And you said that we assume that the sensors are of the same type.
Yeah.
I don't understand that. Can you give an example of sensors of different type?
Oh, sure. Yeah. So I was making a comment to say, let's assume they are all the same, which means that, I don't know, I'm this node, I have one temperature sensor, one accelerometer, one strain gauge. Okay. Okay. Move here. I'm another node. I have one temperature sensor, one strain gauge, one accelerometer. The same sensorial platform, homogeneity. Okay. But in reality, that is not true. What does it mean? I'm here. I'm the node. I have satellite information. I have I don't know, a temperature sensor, and that's it. I move into the other one. I don't have satellite information. I don't care. What I have a strain gauge, tilt meters, and so on. As simple as that. They are not homogeneous, but we treat them and we crunch them in the very simple, in some crunching. So I was just making the assumption that they are all the same, just to have an easier life and easier understanding. As I was saying, that the adjacency matrix was time independent. But in reality, that is not needed, because if you remember the message passing function, in there, the adjacency matrix has index t, which means that at every single time step, if I have a different adjacency matrix, I will process with a message passing accordingly.
Any other questions?
Can you give an example when you have these physical relationships that you mentioned? Where exactly are they? To use them in the model, are they attractive use? Let's say we have a physical relationship to things.
Okay, so if a physical relationship to me means the bottle is on the table. Okay? Okay, on the table. Which means that if I should model this setup, I have the table is one node. The bottle is another one. The mouse is another node. The bottle is on the table means that there is a connection, physical connection, between the bottle node and the table node. That is a physical. If we know that I and Christus, hopefully not, are connected through a chain, that is a physical connection. If in my apartment, I'm interested in forecasting the power consumption in terms of electric load. And in my neighborhood, I want to do the very same because we are part of a smart city. We cannot use GPS signal to tell me where you are. You need to be anonymous data for privacy. So the physical connection is in the cable that is connecting the two of us. So we know that there is a cable, so giving energy to you because we are connected, for instance, and we might even know the length of the cable, and that is an information associated with the edge. Okay, but in reality, we don't care about the physical connection. So, which means that we are more interested in functional connection, which means that if they are physical connected, they are also functionally connected. But the function sometimes, as I said, is strange. So I don't know. We have two metallic objects here and there. They are not related at all because they are different entities. But we know that the temperature is operating on the volume. You increase the volume, you have a dilation. You decrease the temperature, it will shrink if they are metallic objects, you see? So those two entities apparently are not physically related, but they are functionally related parasitically with the temperature. So I have a functional mechanism. You see, that is an example. I would rather say that if you look at all or most of physical sensors, not virtual, not those coming from social networks, they are physically dependent. Then we always do what we always do. We try to compensate with respect to the temperature, with respect to the humidity, with respect to the pressure. We correct in offset and gain. Okay, get rid of that compensation, and they will be all connected. And that is the level you should put yourself if you want to detect faults, for instance, because that is a reality. Then we tend to compensate because we don't want those effects. We don't like that. I mean, if I measure, if I have a strain gauge and I measure what is happening between here and here, you change the temperature of 1 centigrade, and you will see that value, which is fixed, maybe going up and down. Then it will change, of course, because you are changing temperature, but it will change because the physical transducer is affected by the temperature. You don't need to compensate that. That is the real value. So you need to change the classes when you look at the physical reality.
Other questions? Ready to go for lunch? Thank you, Cesare.
Okay, thank you to you guys.